Percepio Tracealyzer. And before I get started, I will just mention a few things about myself. My name is Kristoffer Martinsson. I work as a field application engineer at Percepio, so I'm based in Sweden. I have a background in development tools for embedded system, where I've been working mainly on the debug and trace tools. And I'm just quickly going through a little bit about the agenda for today. And I will give you an introduction to Tracealyzer, and especially for those of you that are not familiar with the tool. And then I will go through some product news that we released in the 4.5 release that was actually released yesterday. And at the end, I will have a demo on the topic of verify and optimize your embedded application using Tracealyzer. And the main part will actually, my presentation will actually be the demo part. And then we'll also have time for questions. So let's get started with Tracealyzer. So the background of Tracealyzer is more like this, that the source code is not the full picture of an embedded application. It's actually the runtime behavior that is what's important in an embedded application. And especially if you have a multi-threaded application that you have, if you use an RTOS, you cannot see the runtime behavior by just inspecting the source code. So you need to have some runtime monitoring. So this is what Tracealyzer is all about. I just give you a short example here that the execution patterns could be very different for a certain task or a thread. Here we just see 4 different execution patterns for one single task in a very simple demo application. But how many patterns there exist in a real world application, more complex application? Yeah, who knows? It could be many, many. So that's the why you need to have some runtime monitoring. And runtime monitoring can be done in several different ways. For example, to the left here, we are talking about instruction trace. And instruction traces, for example, for Cortex-M devices where you have ETM. This is a hardware block inside of the CPU that generates trace information so that you can reconstruct the program flow. So it more or less gives you information on assembler level or source code line level of what is actually going on in the CPU. But the abstraction level here is very, very low. So you see a lot of details, but it's very hard to spot more on RTOS level, on kernel objects like mutexes, semaphores, queues, and so on. It's very hard to spot issues on that level with instruction trace. On the right-hand side, we see application logging. That's the normal printf that most of us are using, more or less providing a log of what is going on by instrumenting your code and outputting a text string, more or less describing what is going on in the system. But in the middle here, we have software event trace. And what is that? It's more of when you have an RTOS that you get events based on different when things are happening in the RTOS kernel. For example, when there is a task switch, when you're receiving data from a queue, etc., etc. And Percepio Tracealyzer is more or less, we are focusing on both software event tracing and application logging. That's our product, what we are focusing on. So Percepio Tracealyzer, here you see a picture of what the tool can look like. But this is the part that runs on your PC, and that's the part that we call Tracealyzer. So, but there is another part in Tracealyzer that is important, and that is what we call the trace recorder library. And that is what is included inside of the embedded application that you have. There are different trace recorder library depending on which RTOS that you are using. So the trace recorder library is responsible for actually generating the trace data or the trace events and store them somehow or send them to the host. This can be done in two different ways. We have something called snapshot, which is more or less a buffer, a ring buffer in the RAM of in the embedded system. It's typically quite small, a few kilobytes or something like that, but it can store a number of events. And when you are debugging your application, you can read the contents of this trace buffer with the debugger. The other option is streaming, and then you need some interface for sending the data to a host during runtime when the embedded application is running. And this can be done in several different ways. We have support for streaming over TCP/IP if your embedded application have these kinds of features that can be used. It could be over a high-speed UART, serial interface. But more commonly, the most common one is if, for example, if you have a debugger from Segger, a J-Link, they have something called RTT. That is another streaming interface that we can use. And also quite common today, it's something called ITM, which stands for Instrumentation Trace Macro Cell. That's available on Cortex-M devices. And quite many debuggers support serial wire trace, and then we can use this to get the data from the target to the host during runtime. So that's Tracealyzer, and I will go into a little bit more about what Tracealyzer actually does here. So here I have three different circles. We have the bottom one, software tracing. That's the basis of everything. So that is what is generated by the trace recorder library in the embedded application. As you can see here down to the right, we just see an example. It's more or less a textual description of what is happening in the embedded application. This kind of logs could be quite difficult because it's quite huge. It's difficult for the human brain and eye to analyze. So we have in the Tracealyzer software something that we call semantic event processing. It's the blue circle here. And what is that? That is more or less, the software analyze the content of the trace buffer, and it actually understand what different events or means. So it's, for example, let's take the queue receive that we see here, one of the events. The Tracealyzer understand what the queue is and what the receive is, so it can connect things together. For example, we have a picture here up to the right of communication flow. So based on the trace data that's come from the target, we can create a communication flow graph saying that there is a task called HMI that sends data using a queue, a control command queue, to another task, a control task, and so on. So that is what semantic event processing means. And then the third part in our software, we call it top-down workflow, which means more or less that you can zoom out to see everything. Maybe you have a trace recording for 1 minute. You can zoom out and see everything, but you can also drill down and see more and more details when you zoom in. So all of this combined is something we call visual trace diagnostics. So that's what our tool Tracealyzer is all about. Okay.
By the way, feel free to ask any question you might have during the webinar. The open discussion.
Yes. Okay. So just give you a few example of when Tracealyzer can be very, very useful. First of all, you can see the right-hand picture here. This is just the main view, more or less, in Tracealyzer. It goes trace view, which is a timeline, more or less, where you can see the different tasks, how they execute, and also all the types of events that has been generated by the code. So you can see, for example, different tasks, how they use different kernel APIs, like here we see queue receive and so on. And also there could be included application logging, or what we call user events. These are what I see here as yellow here in the picture to the right. I will come into more about this in my demo at the end here. But when is this type of debug tool useful, or trace tool useful? Yeah, it's especially when the location of a bug is not obvious. Maybe you have an error handler and you set the breakpoint there, but by just inspecting what's available in the debugger when you hit the breakpoint, you don't understand why you ended up there. Then a trace tool could be very, very useful to analyze, to see what was going on before you actually hit the breakpoint. Also, there are use cases when it's maybe not possible to halt the application with by setting a breakpoint and so on, because it might destroy some communication you have with external interfaces and so on. So then it might be useful also to use tracing. If you compare our recorder library and event tracing here with a normal printf, it's way more effective. Normally it could be 100 times faster if you compare it to a normal serial port, a UART on with 115 kilobaud. Also, the event tracing gives you automatically more or less information about the kernel and the resources in the kernel and so on. That's very, very difficult to instrument on your own to get this information. And also you have the visualization. That's the main thing about Tracealyzer. I just want to mention a few things about the supported platforms. So here are a list of the RTOSes that we support. The most common one is FreeRTOS. There we have our own trace recorder library that you include in your FreeRTOS project. But FreeRTOS, there are many trace hooks that we are using, so to say, so to run our trace recorder library function to generate the trace. And at the moment, we have FreeRTOS normally only runs on single core environments, and we're supporting that. But now it's getting more and more common that there comes FreeRTOS version that supports multi-core or SMP, and we plan to support that as well. We already have a few of these supported. I will mention that in the product news later on. And for other operating systems like ThreadX, VxWorks, and Linux, we actually don't have our own trace recorder. We rely on the trace infrastructure, the software trace infrastructure that is available in these RTOSes. So for example, ThreadX, there is already a trace recorder library. And what we do is that we are just supporting and can analyze that format of the data. So for example, for ThreadX, there is already multi-core support, and that's also true for VxWorks and Linux. And we have a few more operating systems that's not listed here, and one of them I will mention here in the product news. Okay, so let's go into a little bit about product news. What's new in version 4.5 that was released yesterday? The first thing I would like to talk about is DevAlert support. And actually, DevAlert is a completely different product. So that's it's also coming from us as at Percepio, but it's not included in Tracealyzer. But with Tracealyzer 4.5, we have added support for it, and I will show you what that means. But first, I will just briefly would like to describe what DevAlert is and what the use case is for DevAlert. So DevAlert is kind of a digital feedback loop from devices to development. So let's consider a use case that you have 1,000 IoT devices that you have deployed. And you have just pushed out an update to these devices over the air to add maybe a new feature or something else. And just after that, you start seeing that some of the devices start malfunctioning. You get some reports or from the device and that errors or warnings. So you have a few of these 1000 devices that are not working as they should after the update. What should you do? Yeah, normally how you would have like maybe you in your warnings and errors that is sent to the cloud, you might have some alert type indicating what type of issue or warning or error that it is, and you might have some symptoms, some data that you have added more or less in these kind of alerts. But it might be very difficult to reproduce these issues because you didn't see this issue when you tested this in the lab and the testing you have done before you did the release. So what we have done with DevAlert is that we have taken the concept of Tracealyzer and our snapshot recorder, and we have added so that this should be included in all the in devices that it's also deployed out in the field. So what's going on? What will happen is that when there is an error or some warning or something, this is defined by our customers. Then they can also send this information to the cloud, but also attach the contents of this snapshot trace buffer, which is normally a few kilobytes. And then this could be feedback to the development team, and they can analyze it, and maybe they will be able to catch or see what is wrong on those devices. So what we have done in Tracealyzer 4.5 is that we now have support for DevAlert, meaning that we have a dashboard. You see it to the right in the picture, and then top part of the picture here, you see a dashboard with so that the developer more or less, when there is a warning or an error in some device, they can just click on the trace and then download the trace from the cloud and then open it in Tracealyzer and analyze it. So this is DevAlert. And there is actually another use case for this that we see more and more commonly, and that is using Tracealyze in system testing and continuous integration. So in this case, maybe the data is not going to the cloud. It might just go to a computer in the test lab or something like that. So when the development team push code to repository, you have some automatic testing done. And if some test fails, included back in the feedback loop, you not only that it fails, but in the report, you also include the trace. So it can be analyzed in Tracealyzer. And just to show you a little bit how Tracealyze is built up, or how DevAlert is built up. So in your embedded software, you have the normal trace recorder library for continuous monitoring. So you record application events, API calls, task switches, etc. And this is stored in a circular buffer. And then you also have some software for generating alerts, that we call it. This is defined by the customers, when they would like to send an alert, if an error occur or a warning occur or something. And the alert normally contains some kind of alert type, some symptoms, like could be some data value, register values, and so on, and maybe also some firmware information, version, and so on. This is sent to the developer's cloud, so to say, that the normal cloud that the product is connected to. And the trace also is sent to this cloud, and it's stored there in that cloud. So there is no traces going to any perceptual cloud, so to say. But we have a service online in the cloud that a DevAlert service that you see up to the right, where more or less the only thing some of this metadata that is generated should be forwarded there to handle notification to development teams and so on. And then the developers can download the trace from the alert storage in the developer's cloud and so on. So this is the data flow of DevAlert. So that was very, very short about DevAlert. And as I said, with 4.5 version of Tracealyzer, we support a DevAlert dashboard inside of Tracealyzer. The next thing I would like to mention is our support for ESP32 microcontrollers. So ESP32, you maybe have never heard of it, but it comes from a company called Espressif. So they are making communication modules, normally in Bluetooth and Wi-Fi. So and they have a custom programmable core. So you can add your own application in there. So, but these are actually not ARM based. They have another type of CPU core or MCU core called Extensa. So with our support for Espressif ESP32, we have hardware support for Extensa LX6 and LX7 cores. And the hardware support, it's mainly that we have in our recorder library a way to get timestamps from some kind of hardware timer, because we need accurate timestamping. So we use some hardware timer. That's the hardware support. And we have also added support for Extensa FreeRTOS. Because it's a little bit different to the standard FreeRTOS, it's a mix of different versions, you can say, of FreeRTOS. But we have added support for that, and also the multi-core support, because the Extensa FreeRTOS is supporting multi-core or dual core at least, because some of the Extensa cores are in these modules are dual cores. So we have added tracing support for dual cores in this case. But unfortunately, so far, snapshot mode only supports single core, but streaming mode, we also support multi-core. And streaming is using one application trace interface that is available in the tools for the ESP32. Okay, and the next news I would like to mention here is our beta support for Zephyr. Maybe not all of you have heard about Zephyr, but Zephyr is an RTOS intended for the IoT market. So with a lot of middleware for communication and so on. And it's a product under Linux Foundation since a couple of years back. Before that, it was actually run by Intel. And before that, it was Wind River, but now it's under Linux Foundation. So it's an open source project. And in Zephyr 2.6, there's actually built-in support for Tracelyzer. So the trace recorder library could be included in Zephyr by just a checkbox, more or less, in the Zephyr kernel configuration, as you can see here on the slide. And the recorder library that we provide is provided under Apache 2.0 license, so it's open source. But this is still beta, so there are a few issues but the main part is working, but we plan to have full support for this in a couple of months. But we already have customers that are using the Zephyr support in Tracelyzer. Then I just want to mention a few short things about other improvements, and mainly on if you're using ITM. So for those of you that don't know what ITM is, stands for Instrumentation Trace Macro Cell. It's an ARM component. So it's a hardware block, a debug block or trace block that's included in an SoC, and it's almost always included in Cortex-M devices. And we can use that to stream the data out to the host. And we have improved it. We have had support for this for some time, but with the latest release, we have made it added and made it more flexible solution for ST-Link debuggers, so that we can support all STM32 devices with this. Before we just could support just the majority of the devices, but some STM devices are a little bit different when it comes to ITM, so we have made it more flexible to support that. And we nowadays also include an example script for if you would like to use a Lauterbach debugger to stream ITM over a serial wire interface. And actually we have an application note describing how this can be done. You can see this on the link here. It's on our web page. And we have also a beta support for ITM trace using GDB. So in this case, we will attach directly to the GDB server that runs on your host to get the ITM data. So this will make it easier in the future for us to support many different types of debug tools. So it will be more hardware independent, so to say. But this is also still beta, but we have some using it. So that was all the news that I was going to talk about. So now it's time for my the demo part. So my demo, the topic of it is, as I mentioned before, verify and optimize your embedded application using Tracealyzer. And these are a few of the things that I'm going to go through here. So statistics reports to get an overview, CPU, analyze the CPU load, and analyze and verify maybe runtime behavior of a single task, and maybe also analyze service calls like API calls, mutex, semaphore, queues, and so on. And then at the end, I will talk a little bit about custom intervals, which is a very, very nice feature, I would say, if you have certain part of your code that you would like to analyze. It's a very nice feature. So I'm going to switch to Tracealyzer. So, and I'm going to start by loading a trace that I have already recorded. So the trace, by the way, was recording using a Seger debugger with RTT streaming, and it was done on FreeRTOS, running on an STM32L5 CPU. And I recorded roughly 1 minute and 20 seconds or something like that. So this is my recording. So let's say that you got the task to optimize and improve the performance of your application. Where should you start? I would say the first thing I would do is try to get an overview and some knowledge, actually, what the performance is. So you can then look go down and actually optimize a few things. So the first thing or first feature that I think is useful in this use case is the actor statistics report that we find here in the menu. So first of all, what is an actor? Yeah, actor in Tracealyzer is what we call an executable element. So it's normally a task or a thread, but it could also be interrupt service routines and so on. It's something that runs or executes in its own context, so to say. So that is what we call actors. So when you generate a report, you can select which actors that you are interested in, but in my case, I will just create a report for all and show report, and it pops up on the other screen here. So I will just move it in here. So this will just give you an overview of for example, the CPU load and so on. So you see the different actors or tasks that you hear, and you, for example, can see the CPU usage here. So the control task is taking up 7.5% of the CPU load in the entire trace and so on. And there is more information here that is generated in this report. But this is a good way to start to just get an overview of what is actually executed and how much time, CPU time, does different tasks take and so on. So where should we start analyzing and optimizing if that is a requirement? So, for example, if now in my recording, the idle is like 85%. So in my recording, in my demo application, I don't have an issue with high CPU load. But this could be easily spotted here if you have such things. So that is where I would start if I were about to optimize my application. And to go further then, the next thing I would do is that I will maybe take a look at more details about the CPU load and maybe analyze it over time. And how can you do that? Yeah, then you have something called the CPU load graph that you find here. And I'm going to move this window a little bit. So this is the CPU load over time. So we have a time scale down here. So it's time 0 here, 5 seconds, etc. If I scroll here, we can see it's roughly 1 minute and 20 second recording here. And we can see the CPU load over time. And we have the zoom button to zoom out and so on. Here we also see when the different actors or tasks are actually executing. So if I just, and you see the names of them up here, and actually you can actually filter it here if you want to. You could actually just look at the few tasks if you want to, like this. If you're only interested in analyzing one task, you can do it like this. But I will look at all of them. So I will do it like this again. So for example, if we take a look here at this time slot here, we can see a rather high CPU load here, and we can actually see the different tasks that are running. So for example, the HMI task here, it's darker green here, it's executing quite a lot. And if I click on this one, we can see in the selection details to the right, we see some more details about this task here in this time interval. So we can see the interval here, it's 23.6 to 24 seconds. So the interval is roughly 400 milliseconds. And we can see that the HMI task is taking up 14.7% of the CPU load in this time interval. So let's say if you don't understand why this this task takes up so much CPU load at this point of time, you can double click. I'm going to move this window a little bit to the left. You can double click here. And if you notice the trace view to the left, this view here, is actually zoom to the same and actually highlight the same interval here. So you can drill down and analyze further what is going on. So you can for example just zoom in here and so on to see more what is going on here. So here you see when the different tasks are executing, and also different types of events, like it's using some queues and etc. So there is a correlation between all the windows, all the views in Tracealyzer. Okay. The next use case I would like to mention is, let's say that you have an application where you receive some data coming from some external interface, UART, an SPI interface or whatever. And the normal how it's work is that you have some interrupt handler that takes the data, maybe put it in a queue. That is then there is a task that is responsible for processing this data. If you would like to analyze and verify that you actually process this data in a certain time, maybe you have some requirements on it that you need to process it in a certain time, how can you use Tracealyzer to analyze this? Yeah. I would say that for this use case, you would use something called actor instance graph in Tracealyzer. So I'm going to open another view here, actor instance graph. Okay, so what does the actor instance graph show? Yeah, it shows actually quite many things, but I'm going to configure it a little bit. First of all, I'm going to unsynchronize, because I would like to use filter that's specific for this view. And then I will only look at one actor or one task here. So I will remove all of the others. And then I will change the view to no lines like that. So the actor instance graph can display many different things when it comes to timing and execution and runtime of certain tasks. As you can see here, it has something called execution, time, response time, separation, periodicity, and so on. But in this use case, if you would like to make sure that some data is processed in a certain time, the response time is what would be interesting to check here. So So if I select response time, then what does this show? Yeah, the response time is normally quite low here. I can just click on any of these dots down here, and we actually see here in the selection details to the right that the response time is 1.5 seconds for this dot here, or this event here, so to say. But you can also see the average and the highest and the lowest and so on. And as you can see, there are some of them that has quite high response time here. And it might be that you have some requirements and then you can investigate these further. But actually, I'm more interested in actually these. There seems to be some jitter down here because on this one, it was 1.6 milliseconds. And on this one, if I click on this one, it says down to the right here, 2.4. So what is going on here? Yeah, I'm going to double click on this one. And then I'm going to zoom in. And first of all, what is response time? Yeah, the response time is the time from, let's take that use case that I mentioned before. An interrupt handler plays some data in a queue, and then a task should process that data when it arrives in the queue. So the response time is that more or less the time from when the data is available in the queue and the task then would like to run, it would like to execute to handle this data. And then until it completes or go back to sleep, that is the time, that is the response time. So the response time in this case starts from here. This is the response time, the blue part here, the blue rectangle, and it includes two different things. You see the solid green here. That means that it actually are executing. The task is executing. But when it's like dotted green, white here, the start here and here in the middle, that means that it is ready to execute, but something else is executing. Maybe something else has higher priority or something like that. And that's actually the use case here. Here it wants to execute, but it's not allowed because there are some other tasks, the control task and some other task here that execute on higher priority. So the HMI task is not allowed to execute. So it actually doesn't even start to process this data that's come from the queue until down here. And then it actually gets interrupted again by some higher priority task until it completes down here. So the response time is the entire time here. And it's very useful to verify these kinds of timing requirements that you have, I would say. And that's the difference with execution time. Because if we take the execution time, we see that you don't see these jitters down here anymore. And that is because the execution time is only when you have a solid green here. So when the task is actually executing. So then the time where it's ready to execute is excluded. So that's the difference between execution time and response time. This view can also be used for another use case. Let's say that you have a use case where you have something should execute in a certain period. So you should have something that should execute every millisecond, every 5 milliseconds, every 10 milliseconds, or something like that. In the actor instance graph, it's easy to verify if this is the case. So I'm going to switch to another actor here called control, and I'm going to change to periodicity. So periodicity means more or less how often something is executing. So it's the time from when, so actually periodicity from ready is the time from one task becomes ready here, and then until the next time it becomes ready. That's the periodicity. So as you can see here for this control task, it's normally a very, very low periodicity here. It's down on 1 or 2 milliseconds or something like that, but quite often it actually ends up almost at 100 milliseconds here. So if you're interested in seeing more details, why is this happening, you can double click on something and it will zoom to that location. And it's quite obvious what is going on, because yeah, this control task, it's actually blocks for a queue. And then actually I would assume that we have a timeout value of roughly 100 milliseconds until then it's automatically timeout, so to say, after 100 milliseconds. So it's blocks that period of time. So that's the reason why you see different periodicity here for the control task. And just as we have difference in execution time and response time, you have with periodicity, you have from ready and from start. And that's the same thing here. So if you use from ready, then it's like you include the time where the task will wants to execute, when it's ready to execute. And if you use from start, then you measure from the point where it actually starts to execute. Okay, so that was actor instance graph. You might also have use cases where you would like to analyze and verify the usage of different kernel API calls. And how would you do that? Yes, we have a view called service blocking, or service call block. And you can use that to analyze the behavior of when you're using different kernel APIs or kernel resources. So for example, if we take an object here, I'm going to use the motor queue in this case. I'm going to make this one bigger. And let's say you would like to, so we have a motor queue, and you would like to analyze the behavior of when you receive some data from this motor queue. So I'm going to change the line side here again. And just like similar to the previous thing I showed here, we can see quite a difference in the time of how long it actually blocks here. So most of the time it blocks below 10 milliseconds here, but sometimes it blocks almost at 100 milliseconds. And again, you can click on any of these and you see more details in the selection details to the right. So here we can see that it blocks for 9.3 milliseconds in this case, and so on. And you can double click on one of them and zoom to that location to analyze further. So, okay, so let's take the last use case for my demo here. And that is, let's say that you have some kind of control application that controls some kind of machinery, a motor or something like that. And then you have in the control algorithm, it's more like a state machine that could be in different states, maybe starting, stopping, moving, or running, or something like that. And that's the different states that the machine could be in. And then if you would have some requirements, or if you would like to analyze that, for example, how long it takes to stop a machine, then how would you do that? Okay, I'm going to switch to my IDE here and just show you this, because this is what I've done here is I've been using our user events for this. So I have added in my code here, I've highlighted this vtrace print, where I output the state of my machine. So whenever there is a switch between the different states in my state machine, I output it and generate a trace event for it. So as you can see here, it is a switch case statement here, and we see the different states: init, starting, moving, stopping, stopped, etc. And how do you see these in trace recorder or trace analyzer? I mean, yeah, you can see them. You will see them here as yellow here. Now this is something else, but we can also look at this in the event log. And I'm going to filter this one, and I'm going to only look at the system state like this. So here you can see, we see all of these user events describing this state machine. So you have here at the beginning init, and then you go into the state stopped, starting, moving, etc., etc. But let's say that you would like to measure how long it takes to actually stop the machine. Yeah. Then you might be interested to measure the distance between you see the event stopping and you see the event stopped. Here, these two events. And of course, you can just look at the timestamps here and you can roughly see it's 2.6 seconds or something like that, the time it takes here. But if you would like to analyze this further and see all of these events, because it might happen many, many times, and analyze this, you can use something called custom intervals for this. And this can be found in the menu under intervals and state machines. And here I can create a new custom interval. I'm just going to give this a name. I will call it demo. And then I need to define the interval start. And the starting interval, I would say, is when we see the event stopping here. So I'm highlighting it and use selected. Now, so now we see the starting of the interval is here and the end should be when it stopped, like that. Here you can use different filtering and so on, so it doesn't need to be the complete event name and so on. And you have different contains to begin with and so on, so you can filter this in many different ways. But now I just save this, so that means that I have created a custom interval. And I can use the plot feature here to actually show you this. So we can change the view here again, and we can zoom out. So here we get a plot where we actually can see how long does it take, in this case, to stop the machine. And quite often, or just a few times actually, it's only roughly takes 250 milliseconds down here. I can click on one of these to get more detail here to the right. You see the length, shortest, average, and longest, and so on. You see some statistics here, and you see them all. And again, you can get synchronization with the trace view. So, and actually here we see this interval here. It's called demo here. That's the custom interval. So I will zoom in out now to actually see that if I just highlight it like this, this is the actual interval. So it's roughly 230 milliseconds. So this you can use to then zoom in here, analyze why did it take this long and so on. And this of course can be used to verify that you meet the timing requirements that you have, or it might be that you have if you go below above a certain value, it might affect the user experience. So you would like to optimize it to make sure that you are below a certain time and so on and using custom intervals for that. Custom interval is a very nice feature, I would say. And actually there is a news also when it comes to custom intervals in the latest release 4.5 that I didn't mention on the slides, but from now 4.5 release, you can actually import and export them and save them, so to say. So you can send them to a colleague so that he can use the same interval as you are using, and so on. So that was actually the end of my presentation. So so far there hasn't been any questions. So yeah, but if there are any questions.
I have a question. How much memory is used by this util?
On the embedded device, it's yeah, there are a few kilobytes for flash for the recorder library, and then there are a few kilobytes of RAM. And how much RAM is used depends a little bit on. For example, if you're using snapshot, it depends on how big the trace buffer should be. So that sets the RAM usage, so to say. But if you're using a streaming mode, it depends on the streaming interface that you are using. If you're using ITM, for example, for streaming, it's hardly any RAM at all. It's very, very little. But if you're using some other like RTT, you have a RAM buffer of a couple of kilobytes on the targets, so that's increased RAM usage a little bit, but it's roughly on a few kilobytes level. both in Flash and RAM.
Okay, thank you.
What about multi-core support? Are you going to support it with FreeRTOS?
Yes, Microsoft, Amazon, I mean, have, yes, they have like a multi-core edition or a SMP edition of FreeRTOS. It's not official yet, but it's already on GitHub, so it's release candidates and so on. And we actually have started to work to support that. As I mentioned in my slide, we already have SMP support for FreeRTOS for some custom implementation for it, like the ESP32. We have already done that. So we have some of the work needed is already done, but we need to check the details of the official one, implementation FreeRTOS, and support that. So it will be available in the, I would say, in the coming months.
Excuse me, what about ST microprocessors and Azure operating system?
Yes. Azure operating system, that's Tredex, or just a new brand naming of Tredex. So, and we already support it, as I have here. So we support Tredex today, but with Tredex or Azure RTOS, we are today at least we rely on the recorder library that is already included. And for that, we actually already have, for example, multi-core support because it's built in already in this trace recorder library that they have. The only drawback right now with Tredex is that they don't have any streaming support with that. So it's only snapshot. So you can only store trace data in a RAM buffer on the embedded device. But actually we have some work in progress on actually supporting streaming by adding some code of our own into Tredex there to also support streaming for that. But it's already supported.
Thank you very much.
If a customer uses a Kyle, can you stream it through the Ulink?
Yes. Depends on here what operating system you're using. For Kyle, normally you either use RTX, which is their ARM's own RTOS, or you use FreeRTOS. We can support both, but how you stream it is different. So for Kyle RTX 5, we rely on the event recorder that is already available in Kyle. And we are using their kind of recorder library, you can say, and it can be streamed directly to Tracealyzer, and you can display the data and the trace in Tracealyzer. We have already built-in support for that. If you use FreeRTOS, there is also the possibility to use our recorder, and then you can stream it using ITM. We have actually an application note how to do that with a Ulink, Ulink Plus or Ulink Pro, and so on. So we have an app note how that is done, actually. So we support ARM Kyle, both RTX 5 and FreeRTOS.
What about tracing with fast UART at about 1 mega or USB?
Yes. If you would like to do streaming with our recorder for FreeRTOS, for example, the bandwidth that you need, it actually depends on your application, but normally it is enough to have like 100 kilobytes per second in bandwidth. And sometimes, depending on how much event is generated, maybe you need 200 kilobytes, but quite often 100 kilobytes is enough. And then if you have a high-speed UART, that is, the bandwidth could be enough for that. But we don't, since you need to write more or less a custom stream port where it's more or less like the driver how to use the UART. That's you need to write that on your own. but we have the infrastructure available, and there are some like templates of how to do it, because we cannot like support all the different UART controllers in all different MCUs, but it's possible to use. And for the USB example, we support USB CDC, so it's more like a serial UART over USB, and we already have that supported for STM devices. So we have examples and the how it can be done for STM32 devices. For others, yeah, it's possible to do, but this is again would require a custom stream port, which is possible to write on your own.
Thanks.
Okay, thanks a lot, Christopher, for your time. Thanks, everybody. If you have any more questions, feel free to drop an email to Ohad at Sitesys. We are happy to answer. Thanks a lot and have a good day. Thanks, Christopher.
Okay, thank you. Bye,
Thank you very
everyone.
much.
Have a good day.
Bye.
Thanks. Bye.